and it is k minus 1. I really need a break very soon. So I have this. So these are two polynomials. And these two polynomials here are telling me that when z equal to one of these r k, what happened? This thing goes to 0. This thing goes to 0. So this thing here is called the 0. The 0 of this transfer function, of this ht. Okay, these are 0. So 0, that means really where this, and I have as the 4, I have az equal to 0. So that's called the 0. For z equal to one of these PL for this, then I have as, what the az would be? Should have, right? I divide something by 0. I divide something by 0. So then this is one going to infinity. And that's called the pose. The pose. The pose and the zeros. So the pose is the 0 of the filter. So maybe we can go back to this filter. This filter here, this thing here, what is the 0 of this filter? 0, right? It is 0 here. And what is the pose of this filter? I, right? So I have a filter and I can always draw a pose and a 0. So I take a filter and that is the z-plane here, z-plane, and it would have some pose. The pose is always denoted by this. So and on here is the pose, and maybe it has some 0. Right? So filter, and you can see that when I specify a filter, I need to specify this. And I can similarly specify all the pose and 0 and plus a gain factor here. Right? Equivalently. So a lot of the time actually people can specify filter by simply this plot. Where are the pose and where are the 0? Okay. This gain factor and this gain factor. Now, the pose are really the place where the thing blows up. So the pose, can it be inside the reasonable conversion? No. By definition, in the reasonable conversion, the thing had to converge. Give you something, a finite number, converge. So that's why, for example, this filter here, the pose, suppose sitting right here, the pose here. The ROC is from that inside, right? And you see that, excuse me, the pose here is simply, this is another concept, but for this particular system where the signal, the impulse go towards infinity, now I can run from k equal to 0 to whatever value can. And that means I just use xn minus 1 and so on. I never use anything xn plus 2 and so on. And what is the impact of that? The causal, what does causal mean? The causal means if I have run a real-time system, right? I need to predict the stock market, right? Someone come and tell you, like, I can predict the stock market perfectly, right? When simply I just say, but I need to predict the stock market of the price yesterday, right? So that's like I said. You need to predict the stock market. I mean, I can only use information in the past. You cannot use something in the future, right? And that is, because it's real time. I need to make money in real time. Now, if I do the system with a cell phone, for example, I also have to process everything in real time. I cannot, maybe I can wait, but maybe a lot of system, you need to make action right away. You cannot wait, right? So the action cannot wait, that means, so then the system is causal. or let's say cannot wait. And cannot wait to get the future input to compute my system. Okay, so in that form, this is a causal system. This is a causal system. And in the causal systems, if you know about the Z transform, the ROC all the way tend to go outside. They go outside. Right? You go outside because in the summation here, you go through here and the further you go out, the smaller, sorry, the bigger the Z, and because you have a Z minus 1, you have a Z minus, Z minus 1, so you get smaller. So the message, maybe let me put the result here. So, theorem here is a causal LTI system is stable. A causal LTI system. So the system now is causal, right? So it goes here, and it is stable like this guy. And it's causal stable if and only if all the poles are inside the unit circle, right? So the poles is this poles here because all the poles are inside here, and those poles representing the dangerous region, the non-region of conversion, right? The region of non-conversion, and then everything outside that is okay. And if it's okay, and it's everything inside here, then it must include the unit circle. Right? You can think about this picture a little bit. So I leave this. Understand this is proof here as exercise. How about that? Okay? So let's take a short break now for 15 minutes and we come back looking at the filter design. We see that in the Z domain, right? And that can be quite powerful to understand the stability of the systems in the Z domain. So now we're going to look at the filter in a third domain, which is sometimes more important, is in the frequency domain, right? And we would move on to the technique of designing a filter. So the filter, I use the same letter H, but if I'm going to use omega, I assume you know that I'm talking about the discrete time Fourier transform, right? If I put the Z here, you know that it is the Z transform. So a little bit of abuse of notation here, but it's simpler to write, right? A lot of people write E, J, omega for the same, but too much for me. Okay, so we go back to this linear time invariant systems or a filter. And now look what happened in frequency domain. And that's going to give us some guidance on how to design a filter. So we got a signal X here and Y here. And we know there is a very important theorems that saying first Y of omega equal to H of omega times X of omega. Okay, and the second thing is for X and